Have you ever wondered what happens if you go into a black hole? Well, to answer that, we first need to understand what a black hole is. In the vast expanse of the cosmos, black holes are regions of extreme gravitational pull. They're like cosmic vacuum cleaners, possessing a gravitational force so overpowering that nothing, not even light, can escape their clutches. Imagine a star, much larger than our sun, collapsing under its own gravity. This implosion creates a point in space where gravity is so intense that it warps the very fabric of space-time. This is a black hole, a silent predator lurking in the depths of space, invisible to the naked eye. Black holes are mysterious and fascinating. They challenge our understanding of the universe and defy the laws of physics as we know them. Now that we know what a black hole is, the question remains, what happens if we venture into one? Before diving into the heart of the black hole, it's important to understand how these mysterious objects form. Black holes, the cosmos's most enigmatic entities, don't just appear out of thin air. They are the result of a process that begins with a star much like our sun, but with a mass significantly larger. Think about a star that is at least 20 times more massive than our sun. These stars live fast and die hard, and their life cycle is a spectacle of cosmic proportions. The life of such a star is a constant battle against gravity. The star's core is a furnace, where hydrogen atoms are fused together to create helium, releasing energy in the process. This energy, in the form of light and heat, pushes outward and counteracts the inward pull of gravity. This delicate balance is what keeps the star stable for millions, if not billions, of years. But nothing lasts forever. Eventually, the star exhausts its hydrogen fuel. Without this source of energy, gravity gains the upper hand. The star's core collapses under its own weight, and the outer layers are thrown off in a dramatic explosion known as a supernova. However, what happens next depends on the mass of the original star. If the remaining core is about 3 times the mass of the sun, the force of gravity is so strong that it continues to collapse. It shrinks smaller and smaller until it forms a point of infinite density, a singularity. This is the birth of a black hole. Surrounding the singularity is the event horizon. This is the point of no return. Nothing, not even light, can escape the black hole once it crosses this boundary. And so, the black hole sits, a silent sentinel in the darkness of space, waiting for any unsuspecting matter to come too close. Now, with a basic understanding of how these cosmic monsters are born, let's explore what happens when you get too close to one. Imagine you're an intrepid space explorer and you've stumbled upon a black hole. The first thing you'd encounter is the event horizon. This is the black hole's boundary, the last stop on the cosmic highway before the unknown. Picture it like a waterfall, where water cascades over the edge, never to return. That's the event horizon for you, the point of no return. This invisible threshold around a black hole is where the escape speed equals the speed of light. As the speed of light is the cosmic speed limit, nothing, not even light itself, can break free once it's crossed this boundary. It's the ultimate celestial trapdoor. It's worth noting that from a distance, you wouldn't see anything special at the event horizon. But don't be fooled. Once you cross it, you're inexorably drawn into the black hole's maw, forever trapped in its gravitational grip. Crossing the event horizon would be the beginning of a one-way trip. Now, let's talk about an interesting phenomenon that would occur as you fall into a black hole: spaghettification. We've all been fascinated by the idea of falling into a black hole, haven't we? But have you ever wondered what would happen to you? Well, the answer is a bit noodly. Spaghettification, a term coined by the famous physicist Stephen Hawking, describes exactly what would happen to you. It is the process where an object is stretched and compressed into a long, thin shape, much like a piece of spaghetti, hence the name. Here's how it works. As you approach the black hole, the gravity acting on your feet would be much stronger than the gravity acting on your head. This is due to the extreme gravitational pull of the black hole. This difference in forces is what causes the stretching effect. Now imagine this. You're falling feet first into the black hole. The pull on your feet is so strong that they start to accelerate faster than the rest of your body. This is where the compression part comes in. While your body is getting stretched out lengthwise, it's also getting compressed sideways. This is because the gravitational pull isn't just pulling you down, it's also pulling you inward. Think of it as a cosmic Play-Doh fun factory. You start out as a compact ball of dough, but as you pass through the fun factory, or in this case the event horizon of the black hole, you're stretched and compressed until you're a long, thin noodle. But don't worry, this wouldn't happen instantly. You'd have some time to enjoy the trip. As you get closer and closer to the black hole, the stretching and compressing would become more and more extreme, until, eventually, you'd become a very long, very thin piece of cosmic spaghetti. So, if you were to fall into a black hole, you'd become a very long, very thin piece of cosmic spaghetti. If by some miracle you survive the process of spaghettification, you'd eventually reach the singularity. This is the heart, or rather the core of the black hole. A place where our normal understanding of physics seems to take a vacation and where the fabric of space-time itself is twisted to the extreme. So what is a singularity? Well, in the simplest of terms, it's a point of infinite density. Everything that has been swallowed by the black hole, all the matter, all the energy, it all gets crushed down into this infinitesimally small point. It's as if the universe took everything, and I mean everything, and squashed it into a space smaller than a single atom. The gravitational pull at the singularity is mind-bogglingly intense. So intense, in fact, that it warps space and time into what we call a space-time singularity. Here, our everyday understanding of directions, of up and down, of before and after, they all get twisted and turned on their head. Now, you might be thinking, surely our understanding of physics can explain this. Well, that's where things get even more interesting. The physics we understand and love, the laws that govern how apples fall from trees and planets orbit stars, they break down at the singularity. Einstein's theory of general relativity, for instance, which brilliantly explains gravity, predicts the existence of singularities. But, and here's the kicker, it can't explain what they are or what happens within them. It's a bit like knowing there's a room in your house, but having no idea what's inside it because the door is always locked. Quantum mechanics, our best theory for explaining the behavior of particles on the smallest scales, also runs into trouble with singularities. It suggests that they can't actually exist as they're predicted by general relativity, leading to a major unsolved problem in theoretical physics. So the journey into a black hole would end at the singularity, a place where our understanding of physics breaks down. It's a mystery that continues to baffle and intrigue us, a cosmic riddle at the heart of one of the universe's most extreme objects. Now, let's imagine for a moment what would happen after you've been sucked into a black hole. Well, it's not as simple as just popping out the other side in some parallel universe. In fact, the truth is, we simply don't know. There's a lot we understand about black holes, but there's even more that remains a mystery, and what happens after you enter a black hole is one of those mysteries. One of the most puzzling aspects of black holes is the so-called information paradox. This is the conundrum that arises from the fact that information about anything that falls into a black hole seems to be lost forever. This seems to contradict the principles of quantum mechanics, which state that information can never be truly lost. The information paradox has led some scientists to propose the existence of white holes. These hypothetical celestial bodies are essentially the opposite of black holes. Where black holes pull everything into them, white holes would push everything out. Some have suggested that black holes and white holes might be linked, forming a sort of cosmic tunnel or wormhole through space-time, but there's a catch. While black holes are supported by plenty of observational evidence, white holes remain purely theoretical. We've never observed a white hole, and current understanding of physics doesn't predict their existence. So where does this leave us? Well, in a state of uncertainty, to be honest. We know that black holes are incredibly dense, have immense gravitational pull, and that they distort both space and time. But what happens once you've crossed the event horizon? That's a question that remains unanswered. We're on the cusp of a new era of astronomical discovery. With advancements in technology and our understanding of the universe, we are constantly pushing the boundaries of our knowledge. Black holes, once thought to be the end of everything, may just be the beginning of a new understanding of our universe. Perhaps one day, with more advancements in technology and our understanding of the universe, we might just unravel the mysteries of black holes.